Okay, so just continuing on with part 2. Again, we were looking at normal CDF in the first video. We're continuing on with that idea, but we're going to be looking at a few more contextual issues in just a moment. So in order to finish this off, again, we had a distribution n 70 with 3 squared. So we know from that that obviously our mean is 70 and our standard deviation is 3. And we looked at one probability question that had an upper and lower specified for where a random variable lies for us to calculate the probability of. But now we've got just one asking greater than a certain value, what would be the likelihood of that? So it asks us what is the probability that a random value given by x is greater than or equal to 74. So in order to solve this, what we need to do is head over to our calculator again, and remember it had upper and lower and those, so in order it goes lower, then upper, then mu, then sigma. So in order to do this, we type in lower as being 74, or if you don't have the new ROM, you just type in 74 as the first thing, then you do a comma. Then the upper would be e to the power of 99, because that's the highest value our calculator can remember. So again, what I touched up on in the last video was that the lowest value our calculator can do is negative e to the 99. Again, e is where you actually do second function comma. And the highest value that our calculator can handle is e to the power of 99. And again, think about e as being 10 to the power of. So this value here is really negative 1 watts of 10 to the power of 99, and this one here is actually that there. So again, for our upper, we have e99, second function, comma, 99, and then we have mu as being 70 and standard deviation as being 3, and we get the probability of this event being 0.09, and I'll just round it to 0.091. So again, it's roughly 9% of distribution that fits under there. Again, in terms of probabilities, as I said in the last video, we can think of the normal distribution as actually being an area of 1 under there, and then we can break it up depending on the interval at which we want to look for a random variable and the likelihood of it being there. So again, this one isn't a standard normal distribution because, of course, mu is not equal to 0 and the standard deviation is not equal to 1. But again, using calculator technology, we're able to do this even for distributions that aren't standard normal. So now let's have a look at a few contextual problems. So in order to do this, I'm just going to rub off part of the board. Again, the calculator instructions are up in the top corner. But our first question says, the speed of cars passing a supermarket is normally distributed with a mean of 56.3 kilometers per hour. And it says that the standard deviation is 7.4 kilometers per hour. And it asks, find the probability that a randomly selected car is travelling between 60 and 75 kilometre hours. So in order to do this, let's have a think about what our values of normal CDF will be. So again, it's asking between 60 and 75 kilometre hours. So we know that our lower, which is the first value we put in brackets, is of course going to be 60 because that's the slowest car speed we want to evaluate. The minimum, the lower limit. And we know that the upper is of course going to be 75. And now we know that based on the problem, we have a mean of 56.3 and we have a standard deviation of 7.4. So in order to solve this, we just hop across to our calculator, and I'll just make that dot a little bit more evident there. So we hop across to our calculator, again, probably know what to do now, second function, distribute lower of 60, upper of 75, a mean of 56.3, and a standard deviation of 7.4. Click paste, Click enter, and of course we're going to get a probability that a car is travelling that fast is going to be equal to 0.302, and when we actually round that's going to be 0.303. And again, we could write a summary sentence. We could say the probability of a car travelling between, or a randomly selected car travelling between 60 and 75 kilometre hours would be that. Again, a summary sentence generally does help with contextual problems. It makes things a lot clearer, and it makes things a lot nicer, and it shows that you understand the problem. So we could write that out, but for time purposes, I'm going to keep it nice and simple. So next question asks, what is the likelihood that it is travelling a maximum of 70 kilometres? So again, another contextual problem, still with the supermarket and looking at the cars, but we need to fill in our brackets differently. Of course, the last two values haven't changed because we're still on the same problem. So we know that our mean is going to be 56.3, and we know that our standard deviation is going to be 7.4. So now we know that the normal CDF, because it has to be at most 70, we know that 70 kilometre hours is of course going to be our upper limit because of that. And we know that our lower limit must be the lowest value that our calculator can possibly go to. Because again, you could probably have the really, really significant outlier of someone doing 30 Ks or something like that. But in order to accommodate for that, we'd go negative e to the power of 99. And again, e is second function comma. So I'll just plug that into my calculator, second function distribute down to normal CDF. And then what we do is we go second, in fact we don't even need to press second function, so it's negative second function e 99, upper of 70, because again the car is travelling at most 70 kilometres per hour, and then your mu and sigma value should still be in there from the last problem, and you see that it is very likely for a randomly selected vehicle along this road passing the supermarket to actually be travelling at most 70 kilometres an hour. So generally, they're not going above that speed limit. If that was the speed limit of the road, I don't know. But again, a small portion, or a small value of a randomly selected car, would actually be travelling faster than that value. And now lastly, it asks, what is the likelihood of a car travelling at least 60 kilometre hours? So again, it's the same sort of problem, but our upper and lower are different. So at least 60 kilometre hours. So in order to do this, we know that our minimum value, because it says at least, must be 60, and we know that our upper value must be e to 99, because you would probably get some people, very rare, but still some people, who would probably go very, very fast down that road, possibly even hundreds of kilometres. Hoon drivers. So in order to calculate this, again, we go to normal CDF, and it's 60 is our lower, our upper is going to be second function e to 99, and then your mu and sigma should still be in there. So we calculate the probability of someone being at least 60 kilometres to be 0.31. Yeah, 0.31. So again, as you can see there, we can basically calculate how fast a vehicle is going, or what the likelihood of a vehicle travelling at a certain speed will be. We can even choose different intervals if we want to. Say x was how fast the car was going, we could possibly look at 65 to 75, for example. Or we could possibly see the likelihood of some hoon drivers being on the road by looking at greater than 135 kilometre hours. So it's pretty cool to have these normal CDF functions to work out the area under the curve, and hence work out the probability of a value, or a certain range. Okay, so moving on to the next problem, and I'll probably just do one from this question set, depending on how we're going for time. Yeah, I'll do one from there, and then we'll finish up with a little more difficult one. So, let's say the IQs of secondary school students in a particular area are believed to be, and again, IQ, generally the average IQ is around about 100, 105. but in this case the average is 103 for secondary school students in a given area, and a standard deviation of 15.1. And again, this is IQ, which is just a scalar, it doesn't really have any units as well. But find the probability that someone will have an IQ of greater than 140. And greater than 140 by most IQ tests would mean that someone is a genius. So let's see how many geniuses there are as secondary school students in this town. So in order to do this, we'd have our lower, which would be 140. We'd have our upper, which would be the largest value a calculator can possibly handle. However, technically, IQ actually maxes out around about 250. No one's really got that high. But our mean value is 103, and our standard deviation is 15.1. So from that, we can work out how many geniuses there are in secondary school education systems within the area. Again, what the context of the question asks. Second function, distribute, and we go to normal CDF. And of course, the lower is going to be 140. The upper's already in there from the last problem, it's E99. And then we have a new mean of 103 and 15.1 as being the other one there. So the likelihood, or the probability, of a secondary school student having a genius IQ would be 0.00, as you can see there's not many of them, 72. So a very minute set of people. So let's actually bring a little bit more contextuality back to this. Let's say that there are 20,000 people in this town, and we want to know how many, or 20,000 secondary school students, so we're looking at quite a large town, but 20,000 secondary school students, and we want to know how many are geniuses. In order to do this, because this is a probability, so again it's between 0 and 1, what we can do is we can simply multiply the probability by that value there that we just calculated. And if you're having a hard time getting your head around how that works, well, think about it. If the probability of 1 means that everybody, it obviously means that everybody's going to suit that condition, but if we times this by 1 here, we know we're going to get 20,000. So that's how we actually work with probabilities to be able to work out the number of secondary school students who have a genius IQ. Or again, it could be a range of different contextual questions. It could be the length of fish, the length of cod, it could be eggs, it could be a wide variety of different things, nails, bolts, that kind of thing. But if we look at how many are geniuses out of this selection, so it's 0.0072 times by 20,000. Then the number of genius students at secondary school level, or people with a genius IQ at secondary school level, is 144 students. And that may not seem, that might actually seem, a decent amount, 144, but keep in mind that most schools would generally have anywhere between, say, most secondary schools generally have between about 1,000 to 2,000 students. So we're looking at a very large population here. And as you can see, if we actually do the inverse again, so 144 over 20,000, if you just check that out on your calculator, you should get the same probability result as before. Yeah, I actually did it in fractions, so it simplified the fraction for me, which is 9 over 1,250. But again, it's the same as before, 0.0072. So it's a very minute set of circumstances within the population there. There aren't that many geniuses. By proportion, anyway. Okay, and I think that's pretty much it for this video. It looks at normal CDF. Hopefully you've enjoyed the series. Again, if you have any questions, post them below. Yep, so we've looked at some contextual issues, and Hopefully you got a better understanding of the calculate instructions, the upper and lower value. See ya!